Dear viewers, welcome to the course Data Structures and Applications. This is session 5 of module 3. Myself sathisha.ms, Assistant Professor, Department of Computer Science and Engineering, Canara Engineering College, Bantwal, Mangalore. This is the continuation of applications of linked list. You people have already studied the concept of a polynomial, what is polynomial, how to represent the polynomial using linked list, and also you have seen how to add two polynomials using linked list concept. So under this session we are going to study the circular list representation of polynomial with header node, and also we will see how to add two polynomial which are stored using a linked list concept. Circular representation of polynomials. So here one polynomial, that is 3 into x to the power of 14 plus 2 into x to the power of 8 plus 1 is stored using circular single linked list concept. So first we will see what we mean by circular single linked list. So circular single linked list is a linked list in which the link field of the last node is holding the address of the first node. Link field of the last node is holding the address of the first node. The advantage of storing the address of a first node in the link field of the last node is that, so once you reach the end of the linked list, if you wanted to visit again some of the nodes which are present in the beginning of the list, then you can make use of this value and you can come back to the beginning of the list. In case of a simple single linked list, the link field of the last node is always holds the value null. So once you reach the last node, there is no possibility of coming back to the first node in case of simple single linked list or normal single linked list. So if any situation where if you wanted to come back to the first node even after reaching the last node, you can achieve that by storing the address of a first node in the link field of the last node. So that's why it's called as circular single linked list. With respect to the polynomial, each node of the linked list will be having three fields. First field is to store the coefficient, second field is to store the exponent, and even though there are three terms with respect to each term of a polynomial, we are storing only two terms. They are coefficients and exponent. Since the term variable is commonly available with all the terms of the polynomial, while storing the polynomial we are not storing the variable, we are storing only the coefficient and exponent. So 3 is stored in the coefficient field and 14 is stored in the exponent field, and here the second term coefficient is 2, exponent is 8. Third term coefficient is 1 and exponent is 0, and we are storing the address of a first node in the link field of the last node. And with respect to normal linked list, we are maintaining one variable called as a first. First is always pointing to the first node of the list. With respect to the circular single linked list, last node plays a important role. That's why we are maintaining one pointer variable called as last, and we are always making that last pointing to the last node of the linked list. So this is how we can store the terms of a polynomial using circular single linked list. Now erase circular list. So we'll see how to erase the list, that is circular list which contains the polynomial. You people have already studied how to erase a particular node or a particular term of a polynomial which is stored using a normal linked list or a single linked list. Here this function will tell you, tells you how to delete a list which contain a polynomial stored in the form of circular single linked list. So name of the function is erasing circular linked list. That means this function will delete all the nodes or will delete a particular polynomial. So let us see how the polynomial is get erased. First we will see how this is stored, polynomial is stored. So let us take the first polynomial, that is a, coefficient is 14, exponent, sorry, coefficient is 3, exponent is 14. This is the first term, and the second term coefficient is 2, and coefficient is 2, and exponent is 8. With respect to third term of the first polynomial, coefficient is 1 and exponent is 0, and the link field of the last node is holds the value null. So therefore the last node, sorry, link field of the last node holds the address of the first node. So therefore last node is pointing to the first node. So as I already mentioned that with respect to the circular list, the last node plays a major role. In case of a normal or a simple single linked list, first node we are always having the address of a first node. Here we are having the address of the last node. Assume that the PTR is pointing to the last node of the circular single linked list. Last node of the circular single linked list, PTR is pointing to here. So now we'll see how to delete this circular list, that is circular list which contains the terms of the polynomial. So here with respect to this function, they have introduced one concept called as a while. So as you already know that, the in case of a C programming language, the entire computer memory will be divided into three parts. So first one is stack, second one is heap, and third one is permanent storage area. So first one is a stack, second one is heap, and third one is permanent storage area. And as you know that whenever you want to create a node, or all the variables which are created dynamically is going to get the space from the heap area of the memory. So you know, with respect to the linked list, nodes of the linked list are going to be created dynamically. All the nodes are going to be created dynamically. That means all the nodes which are created dynamically comes from the heap area of the memory. So what they are assuming is, uh, when you delete a node of a list, they are go back to the heap. When you wanted to create a node, then you check whether the space is available in the heap area or not. If the space is already available, then you get one node from that available space and make use of that node. So once the node is get used, and if it is no longer required for the program, then you send back the node to the heap area of the memory. So such type of nodes, that is the nodes which are returned back to the heap, are pointed by a while. A while is pointing to the list which contains the free nodes. A while is pointing to node which contains the free node, first node of the free node, first node of the list which contains the freed node. So with that, we are using a while here. If PTR, so if the PTR is null, means there is no list in the memory, so then do nothing. If PTR is not null, in our case PTR is not null, it is pointing to the last node. So therefore temp is equal to PTR of link. You take one variable called as a temp, and make the temp pointing to the temp is equal to PTR of link. Temp is pointing to this node now. So PTR of link is equal to a while. PTR of link is this one. You make that, that means, so assume that this is the available node, that is freed nodes. The nodes which are freed from the program are going to be stored in the heap, assuming that these are the nodes which are freed from the other programs. So this is pointed by a while, the variable a while. A while is pointing to the first node of the availability list. So here it is last link field of the last node holds the value null. So now you need to free this. That means you have to send these nodes to the availability list. So that's why you make ptr of link is equal to a while, means you store the address of this, make the address of this to the link field of this. That means this is going to be pointing to here, then a while is equal to temp. So make the a while, remove this because this is the first node which is pointings to the availability list. So make this pointings to a while, then ptr is equal to null. Make the ptr null becomes after deleting this node there is no nodes are available in the memory now. So we have already freed all these things, so therefore ptr is equal to null. So here avail means availability list. So whenever you create a node you make use of those nodes, your program will make use of the created nodes, and once the usage of the node is gets over, then when you free that node, that means instead of deleting the node we are sending that node back to the heap, so that it will reduce the time required to create a new node. That means it's just like creating a new node, but what here they are assuming is the nodes are already available, readily available in the heap, and when you need a node then you take that node from the heap, and once the usage of the node is gets over, then you send back the node to the heap, and if other program wants the same node, then take that node from the heap and make use of the node, and once the usage of the node is gets over, send back the free node to the heap. So this is how you are going to create this is how you are going to erase the entire circular single linked list which holds the polynomial. Here get node and ret node. So get node function is to get the node from the heap. It will check whether the free nodes are available in the heap area of the memory or not. If the free nodes are available, it will gets you the node, gets the free nodes from the heap to your program, and ret node function will return back the ret node function will return the freed node back to the heap. So here we'll check the name of the function is get node. It's not taking any parameters. So here polypointer node, it will check whether the value of avail is null. If the value of avail is null means there is no free node in the memory or heap area of the memory, there is no free node. If that is the case, it will call the malloc function and it will create a new node. It will create a new node and return that newly created node to the function or your program. If the nodes are already available in the heap, that is some other programs are already created a node, and once the use of that created node is gets over, then they have stored the created node back to the heap. So by that time the variable avail is pointing to the freely available first node of the freely available nodes. So if it is null means there is no nodes are available, so therefore it will create a node, newly create a node and return that node. So otherwise if the nodes are available, then you make node is equal to avail, you take one node, from the free list, and avail will be moved to the next node. So that means assume that you have these free nodes already in the heap. You have already these nodes are created in the heap. These are readily available. These nodes are readily available, and if your program requires a node, this is pointed by a while. If your program requires a node, your program will call a getNode function. So what the getNode function will do? GetNode function will check whether the freely available or readily available nodes are present in the heap or not. So if avail is equal to null means the nodes are not readily available. If avail is not null, nodes are readily available, then you take this node, you remove this or detach this one node from the heap and send this node to your program. So therefore the avail is pointing to the next node, because now this node is used by your program. So once your program done with this node, then this node should be freed, and that freed means it has to be attached to the availability list. That can be done by the return node function. Return node function will return the node back to the heap. So node of link is equal to avail, this is called as a node, name of this is node. So to the link field of this you store avail, then avail is equal to node, then make the avail pointing to this node. So like this. So get node function is to get a node from a heap area of a memory. Before returning a node, it will check whether the readily available nodes are the nodes are readily available or not. If the nodes are readily available, then it will gets you one node. If the nodes are not readily available, then if there is a space in the heap, it will create a new node, and the newly created node will be given to your program. So circular list representation of polynomial, circular list representation of polynomial with header node. So the concept what you have studied so far is the circular list representation of single linked list without a header node. So you can have a node, you can have a node at the beginning of the list. So and you make use of this node. A header node is a specially designated node in which it is always present in the beginning of the node, and it will consist of some special information like number of nodes in a linked list, and length of the linked list, some other special information. If you wanted to store, then you make use of a concept of a header node. So header node is not used to store the actual information, it is used to store some special information like length of a node, etc. This is always present in the beginning of the list, that's why it's called as an header node. This is the pictorial representation of a circular representation of polynomial with header node. So this polynomial we have considered here 3 into x to the power of 14, 3 is a coefficient, 14 is an exponent, and 2 into x to the power of 8 plus 1 into x to the power of 0. And in the previous case we have stored a first node address in the link field of the last node. Here header node is the first node, so that's why the link field of the last node holds the address of a header node. So here the variable header, it's a pointer variable, it's pointing to the header node in the list. So we'll see how to add two polynomial using a header node concept. Adding two polynomial represented as circular list with header node. Let us consider same old example. This is the two polynomial. A is equal to 3 into x to the power of 14 plus 2 into x to the power of 8 plus 1. B is equal to 8x to the power of 14 minus 3x to the power of 10 plus 10 into x to the power of 6. So here this is the header node. First is the header node. Then we have three nodes to store the three terms of the first polynomial. With the exponent field of a header node, we are storing a value minus 1. This is very, very important. We are storing the value minus 1 in the exponent field of a header node. So this is the polynomial A, this is the polynomial B. Even in the polynomial B, header node, exponent field of the header node holds the value minus 1, because this is a circular single linked list. You have to stop at some point of time after you consider all the terms of the polynomial. So we'll see how this function works. Return type of this function is polypointer, because it will return the resultant polynomial. Name of the function is cAdd, circular polynomial addition. It will take two polynomial A, it's pointed by A. So first polynomial is stored with this singly linked list with a header node, it is pointed by A, that's why it's a polypointer. And then second polynomial is stored inside a memory with a header node, and it is pointed by B. And we'll take some more variables: polypointer start A, comma C, comma last C. So start A is pointing to the starting of the first polynomial. This is starting of the first polynomial, that is polynomial A. And C is the resultant polynomial here, resultant polynomial, and last C is pointing to the last node of the resultant polynomial. Then we are using some variables int sum, then done is equal to false. Here this is equal to, done is equal to false. We have declared one variable of type integer, that is done, and we have stored a value false in that. So start is equal to A, I have already declared start A is receive the value A. So therefore start A is pointing to the header node of the first polynomial, header node of the first polynomial. Then header node is not having any important information, so therefore that header node should be left as it is. Then A is equal to A of link, you make the A pointing to the next node. Actual terms of the polynomial is stored from this next node onwards. Therefore, A is equal to A of link means A comes here, then B is equal to B of link means B goes to the next node. Actually, it is pointing to the header node, then it goes to the actual node, it goes to the node which contains the actual term of a second polynomial. Then C is equal to get node. So, as I already explained in the previous slide, get node will gets you the node. So, when I execute a statement C is equal to get node, it will create one node with three fields in it. Name of those fields are coefficient, exponent and link. So, then C of exponent is equal to -1, as I already mentioned that the exponent field of a header node holds the value -1. Then last C is equal to C. So, name of this node is C at this point of time, name of this node is C. I will take one more variable called as last C, and last C is also pointing to the same node now, because this is the only node, first and last node of the resultant polynomial. So, therefore, last C is equal to C. Then here I am using a do while statement. Do, it will not check any condition, it will simply entering into the loop. Compare A of exponent. What is the A of exponent here? 14. 14 is stored in the exponent field of this node. A of exponent is 14 and B of exponent is 14. So, here leading exponent of a polynomial A is 14, leading exponent of polynomial B is also 14. Those two values will be sent to the compare function. So, compare function will return either of three values -1, 0 or 1. You know when it will return -1, when it will return 0 and when to return 1. So, compare function in this case, compare function will return a value 0 because exponent of both the polynomial are same. By that time it will check whether start A is equal to A, whether A is pointing to the header node. So, you keep adding the terms until you reach the header node. So, while considering the terms, we have shifted the A to the next node. We have started with the node which is present next to the header node. So, therefore, start A is equal to A is the condition is not true. So, therefore, it not execute done is equal to true. It is present inside a while loop. So, but in our case start A is equal to A is not true, it is false, therefore, it directly goes to the else part. Then it will add coefficient of A, that is 3, and coefficient of B, that is 8. 8 plus 3 becomes 11. So, if of 11 sum becomes 11 now, if of 11 is evaluated as true. So, therefore, we will call attach function. Attach function will attach the term to a resultant polynomial. So, insert attach function, the attach function is going to create a one new node. We have a statement to create a new node with three fields, coefficient, exponent and link, and to the coefficient field it will store 11, and in the exponent field it will store 14, and to the link field it will store appropriate value, and the link field of this receives the value base address of this node, it goes to the link field of the header node, and last C will be moved to the next node. We will see all these things when I explaining the attach function. So, attach function is gets called here, then it goes to the place where you have the definition of an attach function, and inside an attach function it will create a node and it will attach the term to a resultant polynomial. Then after that, for the next iteration you should not consider these two terms, because these two terms are already been considered and we have attached the result to the resultant polynomial. So, therefore, A is equal to A of link and B is equal to B of link means A will be removed from this, it goes to here next node, it goes to next node. Then B also removed from this, B variable B is also removed from this node, it goes to the next node, it goes to the next node, B comes to here. Then after that the break statement, so it goes to the it will break the switch and it will check while done value here it is false, still it is false only, not of false becomes true. So, it goes back to here and again it will compare the exponent of a leading exponent of a first polynomial. Now, at this point of time leading exponent of a first polynomial is 8 and leading exponent of the second polynomial is 10. So, 8 is less than 10. So, therefore, the compare function will return -1. It matches with the case -1. So, if the case -1, it will attach the term from a second polynomial, that is B, to a resultant polynomial. It will call the attach function, we will call the attach function, and inside an attach function we will create a node and that will attach, the result will be attached to the resultant polynomial. Then B is equal to B of link, B is equal to B of link means, So this term will be removed. That is minus 3. Here it will create a node. Attach function will create a node and it will attach minus 3 and 10 to a resultant polynomial, and this term will be removed. That is b is equal to b of link. B is equal to b of link means it goes to the next node, that is last node of the second polynomial, last node of the second polynomial. And again here it goes back to the next statement, that is switch only, compare a of exponent. Now a of exponent is 8, leading exponent of first polynomial is 8, leading exponent of a second polynomial is 6. 8 is greater than 6, it match with the case 1, it will attach 2 into x to the power of 8 to the resultant polynomial, and it will be get removed. Then again it goes back to here, then leading exponent of this is 0, leading exponent of second polynomial is 6, 0 less than 6, 0 less than 6, it will execute case minus 1. So case minus 1 means 10 into x to the power of 6 will be attached to the resultant polynomial. So then the b comes to the header node of the second polynomial. Then next leading exponent of first polynomial is 0 and leading exponent of second polynomial becomes minus 1 at this point of time, because b is pointing to the header node of the second polynomial. So exponent field in the header node of a second polynomial is minus 1, 0 and minus 1 will be sent to the compare function. So obviously 0 greater than minus 1, it matches with the case 1. So it will attach the term 1 into x to the power of 0 to the resultant polynomial, and this will be removed. Now a comes to the header node of a first polynomial, a comes to the header node of the first polynomial. So it goes to the goes back to the switch statement. So now it will take a of exponent is minus 1, because a is pointing to the header node of first polynomial, b is pointing to the header node of second polynomial. So a of exponent is minus 1, b of exponent is also minus 1. So compare function minus 1 and minus 1 will be get compared. So minus 1 is equal to minus 1. So therefore compare function will return a value 0. It has matches with the case 0. Here in the case 0, before adding the coefficients, it will check whether start a is equal to a. If start a is equal to a means we have already considered all the terms of the polynomial. So therefore done is equal to true, it not goes to the else part, it will execute done is equal to true and then break. When it gets break, when this case break, it goes to the while loop, and in the while loop done value becomes true, so not of true becomes false. Then it will comes out from the while loop and it will execute the statement last c of link is equal to c. So last c means last node of the resultant polynomial. Last c is always pointing to the last node of the resultant polynomial. To the last node of the resultant polynomial, you store the value of c, address of c. What's there in the variable c? You have the address of an header node of a resultant polynomial is available in the variable c, that is going to be stored to a link field of the last node, and then it will return the resultant polynomial. So this is how you can add two polynomial with a circular single linked list which contains the header node. Attach function of circular linked list with header node for a polynomial. Here this function is not returning anything, therefore the return type of this function is void. Name of the function is attach. It will attach the coefficient and exponent to a resultant polynomial. So resultant polynomial, you are sending the address of a last node where you need to attach to the next to the last node of next to the last node you are going to attach. That's why you are sending the address from that attach function, sorry, from the c polynomial addition function. Here before attaching the term, you need a node to store that a coefficient and an exponent. That's why it will execute a malloc function. It will create a temp node. To the temp node, it will attach the coefficient and exponent which has been received from the polynomial addition function, and it will, once the node is get attached, change the link field of the last node, that is which is present before the attached node, and then update the ptr value. Ptr is pointing to the last node. So once this term is get attached, the node which contains the new term becomes the last node. That last node will be pointer will be get updated with that last node. Ptr is equal to temp. So this is how we can add the term to a resultant polynomial by using attach function. The content of these presentations has been taken from these two textbooks. If you have any doubt regarding, if you have any queries regarding this presentation, you can mail me with mail ID provided with this video. Thank you one and all.